personally enjoy teaching, but I don't know if you guys are enjoying watching or no. Anyway, so I'm going to right now to continue and show you. Really, that's our topic starts right now. So the topic for today starts just right now. While the first part, which is about like 50 minutes, was about introduction to geodesy, because simply without geodesy, you will see no reason why we're doing this. So anyway, are we in agreement that the actual shape of the Earth is pretty much like ellipsoid? Can I get you to agree on that? Okay, so this creates a serious problem. Watch this. So if you believe that the Earth very much like ellipsoid, which looks like this, okay, now, and it's a surface of rotation and it's a curved surface. Now, if you remember, what is the shape of our maps? Our maps are conical or ellipsoidal or what? Like our map in simple term is a flat sheet. So here is your flat sheet. So that's your flat sheet. That's your map. Now, where is your feature? Okay, where are the features like the rivers and the trees? So really, your features are really the features are simply folds on the earth like so. Those are the features. Now I'm asking you, how can you do that? So you have a feature that exists on a curved surface while you want to represent it on a flat sheet. How can you do that? Simply you do it using a map projection. And without going into the details for now, have you ever put your hands against the light? Did you ever like hold your hand against the light? Did you see the shadow of your hand? Did you see the shadow of your hand? So really the shadow of your hand is a projection on the wall or something, okay? That's exactly what we will do today. We will try to project surfaces and elements and features which exist on a curved surface, which is the ellipsoid, on a flat sheet. Again, as I said, without the introduction and convincing you and talk about geodesy and the shape of the earth, there is no reason for us to talk about map projection. Okay, now, so here's the discussion. So map projection is simply, the definition is here, it's a transformation. We're trying to transform or project the positions on the earth, and remember the earth is a curved surface, to flat map while maintaining the spatial relationships. Okay, how to do that? I'm telling you, just like, okay, just like when you hold a light source against your hand and receive the shadow on a paper or maybe a wall. This process here is a geometrical process, while we can also use some sort of math to do the transformation. Okay. Now, problem is here, there is a little problem. The earth itself is simply a curved surface. When you unfold a curved surface into a flat sheet, it never happens without distortion. Well, look at your shadow, huh? If you ever look at your shadow, does it match the size of your hand? When you look at your shadow of your hand on a wall, does it match the size of your hand? Does it?
No.
No. Does it even match the shape? Maybe yes, maybe no, it depends. So what I'm saying here is that when you do the projection, taking your features from a curved surface, which is the earth, into a flat map, there are something is going to happen. And I'm going to prove it for you in a second. Just please be patient. Okay? I will prove for you and show you what happens as you take this and you do the projection. Watch this. Here is a picture, a very interesting picture. So here is the black surface, that's your Earth, which looks like an ellipsoid with a semi-major and semi-minor axe. And let's take an example of point B, okay? So point B, where does it exist? I'll zoom in. I'll zoom in. Where is my point B? It's simply on the surface of the Earth here. Now what happens here? Where is my map? My map is this flat surface in blue. And same as we talk about, the your hand example and the shadow. Where is the light source? So let's say I put the light source at the center of the earth. So here is my light source. So the light will go, will hit the point B. Again, it travels on a straight line. Huh? So line will go from the light source to the point B on the surface of the Earth, and it keeps going until it creates a shadow. Okay, your shadow, the shadow happens here. So it looks like the letter, the point letter lowercase b, this point here. It is the shadow. It is the shadow of my point capital B, which is uppercase B. Okay, now forget about shadow. I'm not going to use this anymore. I just try to give you an example. So I'm going to use the expression in our class. So lowercase b is the projection of uppercase b. Remember, the lowercase b is on the map, the uppercase b is on the surface of the Earth. Look at the surface of the Earth. It is a curved surface, while the surface of the map is a flat. Now I'm going to prove it for you what happens to the point as you do the projection. I'm going to talk about the length. So I'm going to take another point O. So point O, which happens to be the North Pole. Please tell me, now between point O and point B on the surface of the Earth, there is a length between the 2 points on the ellipsoid. Once you do the projection, so you don't have uppercase B, instead you have lowercase b. Now, where is the length after the projection? Remember point O, it is the same as lowercase o. Do you agree? Like uppercase O and lowercase o, they are the same. Would you agree?
Yes.
Okay, I'm asking you, the distance between O and B on the map, is it the same as the distance between O and B on the ellipsoid?
No.
No, it doesn't stay the same. There are some distortion. There are some distortion, and we want to quantify. We want to quantify. We want to define a term that defines how much distortion that took place. So that's why I'm going to create here a new terminology called scale factor. I'm going to talk about scale factor in a minute. I'll call it K. So simply, the K is a ratio between the length on the ellipsoid divided by the length on the map. So I'm going to take the length on the ellipsoid. I like divide this by the length of the map. So I'm asking you here, the value of the K, is it equal to 1? I'm not asking you to tell me the value of the K. I'm just asking you, does the
No,
K equal to 1?
no.
Okay, great. And what does it mean K is not equal to 1? I will tell you, K not equal to 1, it means there are some distortion that took place during the projection. When K is equal to 1, it means the length on the ellipsoid is equal to the length on the map, which means no distortion, no distortion. Would you agree?
Yes.
Okay, so you know what? I'll talk about scale factor here because this is kind of misconcept. Some people they simply mix between a scale and a scale factor because in my class you learn about scale. In first year you learn about scale. Is the scale equal to scale factor? You will know that in a minute. But let me tell you things in mathematical perspective. Now, remember the point B, uppercase B, it exists on the ellipsoid, and we can define the location by pair of angles, which is lat long. Lat long, pair of angles, lat and long. While B lowercase, this exists on the map, and we want to find the planar coordinates of point B in easting and northing, and those are in meters. Now, map projection I mean, again, in nutshell, this map projection, I'm gonna zoom in. Map projection, it is some sort of mathematical function, and please don't get distracted by what you see on my screen. I'm just focus on what I'm saying, the plain English. So map projection is simply a mathematical function. I call it here F1. Okay, so a function, somehow function that simply you plug in, you input the coordinates of the point on the ellipsoid together with the size and the shape of your ellipsoid represented by A and B, and those are the semi major and minor axes. Then what it gives you, it gives you here the planar coordinates in meter of the same point projected on the map. Again, there is one equation for easting, another function for the northing. And some of you is okay, where are the equations, Tahir? What are the equations? How do they look like? If you insist, let's do it. If you insist. So I provide here with that link here, and simply the link will take you to this document here, which gives you the math. Okay, I'm gonna put side by side. Watch this. So if you want to find the easting or northing, this is how you do it. Tell me please if you enjoy the math on my screen. Take a minute, okay? I want you to appreciate the math. Huh? Doesn't mean that I'm going to teach you the math, but please take a time and look at how much mathematics you have to do to find the x and y. Watch this. So this one here is your easting and northing. Huh? Those are in meters, and on the right side here you will see this latitude and latitude and longitude. So this is how you do it to find your easting and northing. Do you love it? Enjoy it?
Yes.
If you study, by the way, if you study any higher, like fancy math classes, you will see the bottom one. For example, when you estimate this m here, it is simply the Taylor expansion. I'm not sure if any one of you know about Taylor expansion. But anyway, again, that's not my focus. I'm not really wanting to distract you. All I'm asking you is to take a look and see how difficult that. But again, Tahir, do we have to understand that? Do we have to do that? The answer is no. Good news, huh? No. Why is that? Because simply in ArcGIS stores and programs all those functions, and simply it can do that for you. What really you have to do is know the concept of map projection, but you don't have to really understand how F1 and F2 look like. Really, a nutshell is map projection. It takes it, you input to the function the location of the point on the ellipsoid in terms of flat long, and from the other side, it outputs for you the planar coordinates on my map in meters. Okay, now great. Those are very important for scale factor. Number one, a scale factor is not the same as a scale. Okay? Okay, watch this. So a scale is not as same as a scale factor. Remember, scale is 1 to 1,000, 1 to 100, 1 to 1 million. How about the scale factor? The scale factor is something that ranges around 1 because, again, it's a distortion. It represents how much distortion, while the scale itself is a ratio between a distance on the site and a distance on map. So please don't confuse between a scale and a scale factor. That's number one. The scale that we learn in first year and second year, does it change in the map? The word scale you learn in my class, does the scale change on the map, over the map, or stays the same?
Same. Stay same.
Same. While the scale factor, remember, the scale is constant, while the scale factor will vary. And I'm going to prove it for you right now. What is the scale factor of 0.0? What is the scale factor of 0.0? So if we get 2 points very close to the North Pole, do we have any distortion around North Pole?
No.
Okay, how about as we go away from North Pole, like we're going close to the equator, the distortion will increase exponentially, and that's why the K changes, while the scale itself it's constant. Okay, and I said it here already. I said scale factor changes over the map. Scale is constant all over the map. A scale factor represents distortion. Whenever K is equal to 1, it means we have no distortion, and this happens at 0.0. Distortion can be minimized but cannot be eliminated. This is the most important statement, and I will show you how important this is. I'll say it one more time. Distortion can be minimized but cannot be eliminated. Remember, the fact is our ellipsoid is a curved surface. You cannot unfold an ellipsoid to be a flat sheet without distortion. So that's a fact, mathematical fact. Okay? So all we can do is minimize the distortion. And how to minimize distortion is simply by limiting the use of our map. For example, now look at this blue surface here. can I map with this blue surface here? Can I map area around the equator? Think about, please. Can I map with this situation right now area around the equator? So where is my equator? My equator is here, okay? This is my equator. Can I use this map on my screen to map areas around the equator? Think about distortion. Distortion will be incredibly big around the equator, or it will be small. Again, if you don't follow the discussion, take any point close to the equator and you will see. So for example, take a point for example, here, okay? And simply extend your line until it meets your map. So it will go from this point here and then continue until it meets your map. You can see the more we go to the equator, what happens is, do we get more distortion or less distortion? More distortion. And that's why I'm saying here, if you want to use this kind of map, probably you want to limit your map to area very close to your North Pole. Otherwise, the distortion, you have no control over distortion. Okay, so I'm hoping things will get a little bit clean and clear. Now, what I want to say is that also, as you create your map projection, remember, it's not only about length, not only about length. There are some in terms of geometry, there are some angles and areas and shapes and so on. Now, every map projection, it has some characteristic, okay? So far, you've seen only one kind of map projection where my map is tangent to my sphere or ellipsoid at the North Pole. But I'm going to show you in a few minutes that we have so many of them. Unbelievably large number of map projection. And what I'm saying here is that as you project your point from the curved ellipsoid into a flat sheet, there will be distortion not only for length, but also there will be distortion for direction, for distance, and for angles and so on. Okay. However, what I want to say is that there is not a single map projection that is best for every application. Can you please write it down if you wish? I'm going to say it one more time. There is not a single map projection system that is perfect for all the applications. For example, if you want to, taxation, if you want to collect some taxes, what is the property that you want your map to preserve? And you don't care the other property. I guess the area. So if you want to do taxation, you want to use map that preserves the area, and it doesn't matter if it simply distorts directions or maybe distance. How about if you travel, for example, like navigation, like let's say you're driving, not driving, like let's say you are in a boat or maybe an aircraft. What is the best? The best is, or best criteria, or maybe the most important criteria is directions. So you want to have a map that preserves direction between the lines and doesn't matter if it does distort the distance or the area. So really, there is not a single map projection system that is best fit for all the application. Every system, it preserves some of the measurement and simply distort the others. Okay, you know what? Here is some examples of map projection, but I have more interesting application for you. Watch this. So there is one very nice website that I came across this morning, and it's called the True Size, the truesize.com. Okay, and watch what it does. I'm gonna show you the concept of distortion. So all you have to do here is you type any country you wish. For example, anyone can give me any name. Like for example, I took Egypt, because that's my home. Okay, so I took Egypt here and I selected. Anybody wants to tell me any other country if you wish?
Syria.
Syria. Watch this. So here is Syria. I chose Syria, and I'm going to take Egypt out of the business. So Syria here, you can see this is the border of Syria. And the good thing about this website is you can click on Syria and you can move it anywhere you like on the earth. And I want everyone to watch as I move it and tell me what do you observe. So I'm gonna move it one more time close to the equator. Probably nothing happened, no much you can see. But what if I take Syria, I place it on the North Pole, like put it in Greenland? You won't like it, huh? I put Syria on Greenland, so it's very cold, okay? Do you see what happens? I'm gonna do it one more time. So I'll take Syria from Greenland, I'll move it here. Do you see, guys, what happens as I move my same country from one place to another place on the earth? I need some observation, please. Do you see what happens?
It gets bigger.
It gets bigger. The question is, does really Syria get bigger, or the area is still the same? And why this is happening? Why, when I move Syria close to the equator, it gets smaller, and if I move it to Greenland, it gets bigger? The answer is distortion. So as you change the location, although the area on the earth of Syria doesn't change, doesn't change. It is a fact of moving close to the equator. We have less distortion, and if we go back to Greenland, then we have loss of distortion. Okay. Hopefully everyone can see that. Okay. Now you can see here is few example. If you take one country and then you place it on the equator, it will look smaller. Look, only look, only look on the map smaller. The country stays the same area. However, when you move the country to the equator, it gets smaller. As you move the same country to the North Pole, it gets super big. That's because of distortion. Now, here is our options for projection. I mentioned it already a few minutes ago that we have so many kinds of map projection. What you have seen is only one of them. And what you have seen so far is only the one on the left. So the one on the left is what you have seen so far. Very simple. What you do is you get the map and you make it tangent to the ellipsoid at the North Pole. Is that the only option? Watch this. Remember, have you ever make a cone? Conical shape, conical shape. So this is called conical. Now I'm asking you, can we make a cone out of a flat sheet?
Yes.
Yes, you can. Can you make a cylinder out of a flat sheet?
Yes.
Okay, so what happens here is that we have other option by making cones and making cylinders. And what we do is we still just do the same thing. We do the projection, but remember, you can unfold a cone into a flat surface and you can unfold a cylinder into a flat surface. So what we do, for example, in conical, we get one cone, we make it tangent to our ellipsoid. We do the projection same as this, so this is called the projection. So we choose the center of the projection and then connect to the point on the earth that we know the phi and lambda, extend the line until it meets my cone, then unfold the cone. So this will give you your map. So what I want to say here is that the number of projection system is really so many. And based on this discussion here, we have a planar projection, we have conical projection, and also we have cylindrical projection. So you can see here, we have major classification of projection depending on the map surface, planar, conical, cylindrical. Now, so you can see here, this is the planar or sometimes called azimuthal. This one is more popular, planar projection. And we have, this is the earth. So look at this. This is the earth map in a planar projection. Okay. How about conical? So conical, we get a cone, make it tangent to the earth, and simply we do the projection. Now I want to explore with you guys, where do we have zero distortion? Very important, So whenever you have a planar projection, can you tell me here, I'm going to zoom in, where do we have zero distortion, where k is equal to 1 in this grid here? I'm going to point and please tell me yes or no. I will give you some help. I'm asking you, does this point here have zero distortion? It means k is equal to 1. I need some help.
Yes, K equals 1. There's no distortion in our spot.
Okay, perfect. So now let's go to the conical. So the conical, you can see we have we can touch or make our cone touch in this circle here. This is called the parallel of latitude. Okay, this circle here called the parallel of latitude, where it touches where the sphere or the ellipsoid touches the cone. I'm asking you, any point along this parallel of latitude, does it have any distortion?
Yes.
Again, I said this circle here, it is where the cone touches the ellipsoid. So that it's the same circle, it is common between the ellipsoid and common between the cone. So along this parallel of latitude, do we have any distortion?
No.
No. So yes, so there is no distortion here, and the k is equal to 1. How about this one here? So this one here is a cylinder where I got one flat sheet, wrap it into a cylinder, and make my cylinder touch my ellipsoid in equator. So in the equator here, I'm asking you, along the equator, do we have distortion? Remember, the equator is common between the cylinder and the ellipsoid. Do we have distortion along the equator?
No.
True, thank you. And the k is equal to 1. Anytime the ellipsoid and the this map, they share a line or point or a circle along the point and the line or the circle, there is no distortion, and the k is equal to 1. As we go away, for example, watch this. If I go away from this point, what happened to my distortion?
Increasing.
Okay, how about the conical? If I go this way or I go this way, what happened to my distortion?
Increase.
How about if I go here or I go here around the equator, increase? Okay, now why you need to understand this? Because simply if you want to use one kind of projection in one area on the earth, you have to be mindful of where I have no distortion and around which distortion will be minimum. For example, watch this. If I want to map a country that mainly extending east-west, east-west, okay, what should I do? I think if you map a country extend east-west, for example, like Russia, then the best is conical, because simply look at this. If I map a country extending east-west, okay, east-west, what should I do? I should simply use conical, because conical, I'm going to choose one cone that passes through half of the country, like so, like this one here, and this will ensure my distortion will be minimum. How about if I have a country extend east-west around equator? Country extending east-west around the equator. Should I use planar projection? Should I use planar projection if I have country extending east-west around the equator? Should I use planar projection or cylindrical? I should use cylindrical projection, because again, your ultimate goal is to, because distortion will happen. We have no choice. Distortion will happen because you cannot unfold an ellipsoid into a flat sheet without applying distortion. So distortion will happen. The best I can do is minimize it. Minimize it how? By understanding where are the points or the lines or the circles that they have no distortion. Around this area, simply there is no distortion is minimum, and which is something I want to do. Okay, now let's move on to the our last part of our lecture, which is watch this. So you can see we have seen so far, we have seen classification of projection depending on the map surface: planar, conical, cylindrical. I'm going to show you right now that you can take any of those and do some tweak, and what happened, this tweak will create a new projection system. For example, watch this. So this is a projection system which is using a cylinder where the axis of the cylinder is the same as the axis of the rotation of the earth. One more time. This is here in this picture. It's a cylindrical projection. So it's a cylinder. While the axis of the rotation of the cylinder is the same as the axis of the rotation of the Earth. Do you agree?
Yes.
Okay, what if we rotate the axis of the rotation of the cylinder 90 degrees? So 90 degrees. So we take a cylinder, but instead of touching the cylinder on the equator, we simply take the cylinder and turn it 90 degrees, rotate 90 degrees. What happens is we get kind of a projection called transverse, not normal. So this one is called the normal cylindrical, and this one is called transverse cylindrical. Okay, and this is will be our discussion today now. In between, you can turn your cylinder by a certain angle between 0 to 90, and you get a third one called oblique cylindrical. This is not really very common. Really, what's most important is this one. I need to ask you one question before we start. Anyone in my class heard, whether in other classes or industry, or maybe you have a school before, did you ever hear the UTM? UTM, if you did, please show your hands. Show your hands. UTM. UTM. No one? Okay, so I'll show you right now. We're gonna go through the most important one called UTM, and I will show you what does it mean in a second. So what is UTM? UTM is universal transverse Mercator. And every one of these words, it has meaning. Universal, it means this projection system, it covers basically the entire globe, almost entire globe. Okay, you can see this is the entire globe. It goes from 180 west to 180 east in terms of longitude. In terms of latitude, it goes between -80 to 84, pretty much the entire Earth, because we're still missing here 6 degrees north and then 10 degrees south. Nobody lives there, so it's okay. Okay, so at UTM, it's a kind of projection system, universal. It means we can use it almost everywhere on the Earth. What does it mean, transverse? We said it already. Transverse, it means the cylinder is rotated by 90 degrees. 90 degrees. That's the meaning of transverse. And then finally, Mercator. Mercator is the person that he invented this projection. And guess what? This guy was not really a surveyor. This guy was a mathematician. He was a mathematician, and this concept of projection in general is simply a concept come from math. Even the image, you guys remember photogrammetry? Photogrammetry? Anybody still remember photogrammetry? Photogrammetry is a projection. You're projecting your 3D object into two-dimensional image. So photogrammetry is a projection into an image. But anyway, Mercator was a mathematician. He invented this projection, so you called UTM. So U for universal, T for transverse, and M for Mercator. And you can see what happens. Let me remind you. I need some help, please. When we rotate the cylinder by 90 degrees, when the cylinder is in the normal, where does it touch our ellipsoid? Anybody knows? Where the cylinder is a normal position, where does it touch the ellipsoid?
The equator.
The equator. How about if we rotate by 90 degrees? Simply, I'll give you the answer for the sake of time. It simply touches the ellipsoid in a meridian, okay? And then we call it central meridian. And guess what? Along the central meridian, as we agree, there is no distortion, so the scale factor is equal to 1. As we go away east and west of the central meridian, distortion will start to increase, which is something not desirable. And that's why we cannot use one single cylinder to map the entire globe. Yes, we can map an area around the central meridian, but we cannot use it to map the entire globe. How can we solve that? Simply, what we do is we simply will have to keep rotating our cylinder by the zone width. Okay, so we look at this. That's the end. So we split. So I'm gonna draw for you. Here is my central meridian. Let's take one zone, for example. So here is my central meridian, the one in red, that's central meridian. And we said central meridian, we have no distortion, no distortion. And as we go a little bit to the east or to the west, what happens to my distortion? It will increase. And then what we do is, when we come to one value of central of distortion which we don't accept, what we do is we simply need to rotate our cylinder, and this will create for you another adjacent zone like this one here with another central meridian, and we split the entire world into many zones. So let me show you. You guys know that the entire world in terms of longitude from here to there, this is a 360 degrees. Would you agree? 360 degrees. Okay. So it was universally agreed that the zone width was 6 degrees. They agreed a long time ago that from this point to this point here, this is 6 degrees. Okay. Now I'm asking you, if the zone is 60 degrees, so 3 degrees west of the central meridian and 3 degrees east of the central meridian. So how many zones in total? You can count, you can do the math, 360 degrees divided by 6. So this will give you total of 60 zones. You can see the first zone start here on the west. So the border of the first UTM zone starts from 180 west, and again you keep adding 6 degrees until you come to the other side of the globe. So that's zone number 60. So you're kind of splitting the entire world into 60 UTM zone, where every zone is 6 degrees centered around central meridian, so 3 degrees east and 3 degrees west of the central meridian. Okay, now let's look at Canada. What kind of UTM zone covered in Canada? So we start here from zone number 7, and zone number 8, 9, 10, 11. Remember, every zone has 6 degrees in longitude wide. Okay, all the way to zone number 22. Zone number 22. Now, probably we can take a look at Alberta, and I'm pretty sure the quality is not great. So watch this. So this is Alberta. Okay, Alberta is from here to there, to there, to there, to there, to there. Okay, so this is Alberta. I don't know, it didn't work very well, but I'll do it one more time. So quickly from here to there, to there, to there, to there. So roughly this is Alberta, okay? This is Alberta, and you can see Alberta is covered by 2 UTM zones. 2 UTM zones, zone 11 and zone number 12. Let's look at the boundary of zone 11 and 12. Okay, you can see here, zone number 11, it starts from 120 degrees longitude all the way to 114. And then zone number 12, it goes from 114 west to 108 west. So you can see, 6 degrees between 114 and 120. And then also another 6 degrees from 114 and 108. Now, with the central meridian, obviously here is, any help? How much will be the central meridian for zone number 11? I guess 117, because that's in the middle of the zone, 117. Okay, now, where is Calgary? So you know Calgary, the coordinate of Calgary is 114 west. So where is Calgary? Calgary, the longitude is 114, which means Calgary is somewhere here in Alberta. So I'm asking you one simple question, and this answer is based on everything we discussed so far. If we have a Calgary map, does it have high distortion or low distortion? Calgary map, if I tell you Calgary is 114 degrees longitude, and zone number 11, it goes from 120 to 114 with the center meridian in the middle, 117. I'm asking you, Calgary map, does it have high distortion or low distortion?
High.
Yes, Calgary has the highest distortion because we are on the border of zone number 11. Zone number 11, that's why we have the highest distortion. Okay, we're getting very, very close to the end. Now, a few things I want to mention before we end our this class. We have 7 minutes and I'm pretty sure we can finish it. So you can see, UTM splits the entire globe by how many zones? 60 zone. Every zone is 60 degrees, sorry, 6 degrees. So UTM splits the entire globe into 60 zones. Every zone is 6 degrees. That's UTM. Okay, but you know what? There are some other projection called 3TM and 10TM. Watch this, 3TM and 10TM. And I know some of you already guessed it. When I say UTM, it means 6, no change. UTM, it means 6 degrees wide zone. While 3TM, from the name, it means it is the zone width is 3 degrees. And also there is 10TM. It means the zone is 10 degrees. And I know some of you right now are questioning why this is happening. Why people do you want to create something like 3TM and something like 10TM? Here is the answer. I'm asking you, 3TM, and I said 3TM, it means the zone is 3 degrees wide. Which one will have more distortion, UTM or 3TM?
UTM.
UTM, because it's wider, it means more away from central meridian, it means UTM will have more distortion. So you can see here, as I wrote it on my slide, 3TM will have less distortion because the zone is 3 degrees. So this makes sense, and you can see ultimately the zone, we're looking for minimum amount of distortion. Great. Now, some of you will say, okay, what you're gonna say next is contradictory to what you said in a minute ago. Why people then create 10TM? Why? If it makes sense to create 3TM, it means we have a narrower zone, it means less distortion. So why people they go to the other side as well? Like why people they create 10TM? This is not really easy question, So 10TM, it means the zone is 10 degrees wide. It means for sure it has more distortion than UTM, and 3TM, that's more distortion. But the problem is, or sorry, what's good thing about the 10TM, it simply covers wide range, which means you can see, if I go back to this slide, you can see here, Alberta start exactly at zone number 11, so go 6 degrees, and then another 4 degrees. So Alberta, I'm going to put it here, Alberta, if you want to see entire Alberta in one map, in this case, you cannot do that in UTM. You cannot do that in 3TM, while you can do that in 10TM. Because in 10TM, we have a width of between here and there, we have 10 degrees. So this number is 10 degrees, and we can show the entire Alberta in one map. For example, let's say you have a project and you want to show all the roads in Alberta. All the roads in Alberta. Can you do that in UTM? Can you do that in 3TM? No, you cannot. You must go to 10TM. Now, last part. I know that you guys, this is super heavy. So the last part is something called false easting and false northing. And let me explain for you what does it mean. So the UTM, it simply have, after you project it, this line here is your x-axis. And this is your equator. So this is your equator. And this line here is your central meridian in the middle of your zone. And this one is your y-axis. So this is y, or n, forget about y, let's make it n, and this one is your x. You know what happens if this is the coordinate system on your map? There is a little problem here. The problem is this area here, I know some of you won't see this as a problem. This area here, it has negative x coordinates. Would you agree? This area here will have negative x coordinates. So the 0, 0 is the intersection between the meridian and the equator. So this quarter here, it has a negative coordinates in X, while this area here, it has Y negative. Everything under the equator, it will come as negative coordinates in UTM. And so what happens here is that surveyor, they dislike using a negative coordinates. Dislike. Is there anything I can do to eliminate negative coordinates? I
Move the
simply can
origin.
do that. Very simple. I can simply add a positive constant, which will simply shift everything on the positive side. One more time. If you see my coordinate system, so the central meridian will be the north, and the equator will be the x, and the 0, 0 origin is here. What does it mean? It means everything here is positive, x and y. Everything on this quadrant here is x is negative, y is positive. Everything here, the y is negative. Everything here is the y negative, okay? And that's why people, they found a simple solution. If you add a number which shifts everything, simply you get rid of negative value. This number called false easting and false northing. And here we go, huh? Look at the numbers. So for the north hemisphere, I'm going to start with the north hemisphere. So that's north hemisphere. In the north hemisphere, do we have any problem with the northing? Anywhere above the equator, do we get any negative value for the northing?
No.
And you can see I don't have to do anything, so 0, 0, okay? I don't have to add anything. While all you have to do is you just add this number here, 500,000 meter. If you add 500,000 meter to all the coordinates in UTM in the north hemisphere, you will never see any negative value of the easting in the north hemisphere. For the southern hemisphere, we have a problem of both. We can see negative coordinates in X and Y, and that's why in the southern hemisphere, we simply have to add also a false easting and a false northing, but the values are different. The X, we add the 500,000 meter, and for the northing, we add 10 million meter. 10 million meter, okay? And remember, the false easting and false northing, they have no relationship to distortion. All they do is eliminate the existence of negative coordinates. Negative coordinates. And that concludes our class. I'm hoping that I was not that boring or annoying. Okay? Let's see Ryan. Ryan, did I teach you
Oh,
anything more
yeah,
than
I
what
did.
you get?
I did learn for sure quite a bit more. Thank you.
No problem. Okay? Did anybody enjoy this class? Don't be shy. Say I don't enjoy. I know it's very boring, very difficult topic, but I can tell you, when you graduate, and I can tell you one story quickly in 1 minute before I let you go, there is one problem. They have built one bridge. So remember, the bridge is built to be like a steel bridge. And this was in Calgary. And guess what? They tried to put the steel bridge, and the steel bridge is short of few centimeters from the length. Remember, before you put the bridge, you must put the piles and the piers. And can you imagine the problem when you fabricate a steel girder and the steel girder comes short of few centimeters? Can you guess why? The problem is the scale factor. Remember, the designer will work on map, and the map is already projected. It means it doesn't show the actual distance on the ellipsoid. It is just show a distorted one. So when you do a design on a map which already has a scale factor, remember, when you try to lay out these on site, you must reverse the process. You must come up with the length on the ellipsoid. I'm hoping that you guys are following the discussion, but it's so serious. Outside this class, I bet you that you understand the meaning of scale factor. I'm hoping it was useful for you, and I'm hoping it was not that difficult. Thank you so much, and have a great day.
Taher,
Go ahead.